Class, in this video, we pick up our discussion on section 6.4 in your textbook on the inverse trigonometric functions. And so we're going to start here at the top of page 11 in your note packet. In the triangle shown, the angle theta can be defined using the inverse sine function, the inverse cosine function, and the inverse tangent function. So here's the angle theta. Here's the 90-degree angle. So you know this side is the hypotenuse and has length 10. This side is adjacent to the angle theta and it has length 6. This side is opposite the angle theta and it has length 8. So we know that the sine of the angle theta is opposite over hypotenuse. So the sine of angle theta is equal to 8/10. So that means the angle theta is equal to the inverse sine of 8/10. The cosine of angle theta is adjacent over hypotenuse, which is 6/10 in this case. So that means the angle theta is equal to the inverse cosine of 6/10. The tangent of the angle theta is equal to 8/6. Right, opposite over adjacent. So the angle theta is equal to the inverse tangent of 8/6. So using your calculator, making sure it's in degree mode. If you do type in the inverse sine of 8/10 and the inverse cosine of 6/10 and the inverse tangent of 8/6, in all three cases you'll get theta is equal to 53.1 degrees in this right triangle over here. So now let's evaluate some examples where we're taking the composite of a trig function and its inverse trig function. So back in section 2.7 in your textbook, we studied composite functions, and we defined the composition of the function f with the function g is written with this notation and is defined by the equation the composition of f with the function g as a function of x is equal to f of g of x. Right? This is read f of g of x. X is the input to the function g, and then g of x in turn is the input to the function f. G is called the inner function because it's inside of f, and f is called the outer function because it contains the function g. So we're going to do some compositions with trig functions and their inverses. So here we have, if f of x is equal to the sine of x and g of x is equal to the inverse sine of x, then the composition of the function f with g as a function of x is equal to f of g of x. In finding this composition, you know, the first step is to replace g of x with what it's equal to. Well, g of x is equal to the inverse sine of x, so replace g of x with the inverse sine of x, which we have here. Now we have to evaluate f of the inverse sine of x. Well, to do that, we replace x in f of x with the inverse sine of x. So on the right hand side here, replace that x with the inverse sine of x, and we have the sine of the inverse sine of x. So the composition of the function f with g as a function of x is equal to the sine of the inverse sine of x. To evaluate this composition at x equals 1, we have to find f of g of 1. Well, g of 1 is equal to the inverse sine of 1, and then f of the inverse sine of 1 is equal to the sine of the inverse sine of 1. And so we're going to be evaluating compositions of this type on this page. So in the exercise down below, you're asked to find the exact value of each expression. So the first one, we got to find the sine of the inverse sine of 1/4. Now, because sine is the outer function, we know the answer is going to be a number, not an angle. Well, from page 3 of your note packet, where we defined the domain and range of the inverse sine function, it states in the rectangle, if the angle y is equal to the inverse sine of 1/4, then the sine of that angle y is equal to 1/4. That's on page 3 of your note packet. So if we replace y here with what it's equal to, the inverse sine of 1/4, we have the sine of the inverse sine of 1/4 is just equal to 1/4. So the sine and the inverse sine undo each other or cancel each other in the composition, and we just have the sine of the inverse sine of 1/4 is equal to 1/4. Now, in the examples that we're going to be working, where the trig function is the outer function and the inverse trig function is the inner function, as long as that number going into the inverse trig function is in the domain of the inverse trig function, the trig function and its inverse will cancel in the composition. So in this next example, we're taking the sine of the inverse sine of -3/4. Well, the domain of the inverse sine function are the numbers from -1 to 1. Well, -3/4 is between -1 and 1. So the sine and the inverse sine cancel in the composition, and the sine of the inverse sine of -3/4 is just equal to -3/4. In the next example, we got to find the sine of the inverse sine of 5. Well, 5 is not in the domain of the inverse sine. 5 is not between -1 and 1. The domain of the inverse sine is the numbers from -1 to 1. And since 5 is greater than 1, inverse sine of 5 is undefined, and so this composition is undefined. Next, we have the cosine of the inverse cosine of 2/3. Well, the domain of the inverse cosine function are the numbers from -1 to +1. 2/3 is between -1 and +1. So this composition is just equal to 2/3. Cosine and inverse cosine cancel in the composition. The cosine of the inverse cosine of -1/5. -1/5 is between -1 and +1. So the cosine and inverse cosine cancel in the composition, and this composite is just equal to -1/5. Next, we have the cosine of the inverse cosine of -3/2. Well, -3/2 is equal to -1.5. So -1.5 is less than -1. -1.5 is not between -1 and 1. So the inverse cosine of -3/2 is undefined, and so this composite is undefined. And then next we have the tangent of the inverse tangent of 5. Well, the domain of the inverse tangent function is all real numbers, from -infinity to +infinity. So the tangent of the inverse tangent of 5, tangent and inverse tangent cancel in the composition, and so this composite is just equal to the number 5. And similarly, in the tangent of the inverse tangent of 3/2, domain of the inverse tangent function is all real numbers, so tangent and inverse tangent cancel in the composition, and this composite is just equal to the number 3/2.